Hi, I'm Joe. I work here at Lyst. I'm going to talk about, sort of similar to the last one, how we serve recommendations with low latency at scale. What is Lyst, for anyone that doesn't know? There was a brief introduction by Joao. We're a fashion search engine, a fashion aggregator. We scrape all the other retailers on the web, anyone that sells any sort of fashion items. We put them all in one place, let you search for it, let you find things, recommend items that you might like, essentially let you buy all sorts of stuff. We have an iOS app, we have mobile web, we have desktop. This is our site. Great. How do we use recommendations? Okay, how do we use recommendations? So we have product pages. You can see up at the top there's a product. We'll do recommendations that are like more things from this brand, more things from this store, products that are similar to this product. We also do related searches. So this isn't recommending specific items. It's you searched for this, I'll recommend some other search that might interest you. A lot of these tend to be just a designer in another category, or a designer in a subcategory, colors, things like that. We have all sorts of entities for different sorts of things. Related products, same thing as before, just these products are like these other products. How are they related? We have different models that can do different ways. It's either semantically the same, or people that click on this clicked on that. We also do personalization in the app. So we have, these are items that we think that you personally will like. We do these sorts of recommendations as well. So how do we make these? This is the only slide that I'm going to talk about how we make them, because I'm a software engineer and I want to talk about how we serve them, not how we make them. So pay attention. We use LightFM, which is an open source matrix factorization model that we built a few years ago here at Lyst. You can check out the URL at the bottom. It's based on both the features of the entity, the metadata about the product or the user or anything else we know, and also user interactions. So this is the 3 users clicked on this and then also clicked on this other thing that says they're related somehow. We use these to build vectors of embeddings for all sorts of things, as I mentioned, products, categories, brands, stores, users, colors, everything else you can think of on the site. Everything gets a vector, everything's comparable to everything else. We do use cosine distance between the different vectors. That gives us the measure of relatedness. The closer they are, the more they're related. So for serving these, we first set out to just write down our requirements of what do we need to do at a bare minimum in order to serve these, so we could figure out what we wanted to build. So for the service, the first thing we wanted is low latency. We want it below 50 milliseconds. I'm not saying we want to do 50 milliseconds. If you give me 3 milliseconds, I would be even happier. As fast as possible, but anything over 50 milliseconds is just way too slow. We do this as part of our normal website rendering. So this is not the entire page. This is usually a sidebar or a bar down at the bottom of the page. Sometimes we do 2 or 3 at once. If you start doing 100 milliseconds, 200 milliseconds each, it adds up very quickly. We have to handle around 100,000 requests a minute. This is just kind of a number I made up at some point. Based vaguely on the scale. Some of these numbers are changed to protect the innocent. But this is around the number of requests we have to handle per minute. We can't do planned downtime. I have seen some different ways of serving embeddings before that require you to shut off the server at night, reload all the new embeddings in, turn on the server again. We can't have 10 minutes of downtime. We can't have 5 minutes of downtime. We serve customers around the world 24 hours a day, 7 days a week. So we can't just deal with that. It has to be able to run AB, ABC, ABCD tests. I want to be able to run lots of different sources of embeddings at the same time. If one of my data scientists thinks he can come up with a better way to make embeddings, and he thinks it's going to be better than the old one, I want to be able to just do a 50-50 test, 25, 25, 25, 25 test. Whoever wins, turn that one on, kill all the rest. We move on. This last one isn't really a requirement as much as just something I wanted, which is the serving infrastructure separated from the recommender itself. This ties into the last one, which is I don't care where the embeddings come from. I don't care what model we use to build which embeddings. we should have one server that can serve all of the different embeddings. As long as they could be compared with cosine distance and they're a vector of floats, we can serve it. So next, entities. I mentioned these before. We have a lot of different ones. One thing I didn't quite mention is we do comparisons between entity types. So we have an embedding for each user, which essentially is the perfect product for that user because you can then compare it to other products. So all of these different entity types can be put together. The only reason I mention it is you can't just shard them. You can't just put all the users here and all the products here because you have to do comparisons between them. This is just the scale. We have tens of millions of entities. Mostly it's products. We have tens of millions of products at any given moment. We have to compare between them all. This leads into a lot of the decisions we make down the line just because of how many things we have to compare. Filtering. This is probably by far the biggest thing that limits how we actually implement it. We filter entities by metadata all the time on the site. Much of how you do searches, much of how you find what you're looking for is by filtering. So on the right there, you can see some of our filters. There's actually a couple more down below the fold that don't even fit. Do you want things that are black? Do you want things that are blue? Do you want things in your size, in a certain material, from a certain brand? You want only Gucci? You want only Balenciaga? You want only red Balenciaga trainers? That's exactly what you want. Fine, you can filter things down. One of the special filters is the country filter, which is essentially, what country are you in? Because we need to know what items will ship to you. Every one of the stores that we scrape and have on the site will only ship to some countries. Nobody ships to every country. The average product is in about 35 countries. So a lot of our products are in multiple countries. But this is a filter that's kind of always on. So at the bare minimum, we have one filter, which is country. Everything else gets applied on top of that. And I just want to talk for a second about relatedness versus filtering. So relatedness finds things related to some target. So I have here a red dress. I want to find things that are related to this red dress. It's mostly other dresses. None of them is really red. I mean, the second one maybe, I don't know. The second thing is filtering. Filtering finds only things that are in that filter. So you can say, just find me every item that is black dress on the site, right? And this is an absolute thing. If you're in that filter, you have to be a black dress. We can't let things slide in that aren't black dresses. We can't just find things that look like black dresses. It has to be a black dress. And then the interesting thing is when you put these together, because you can say things like, find me all the items that are related to this red dress, but that are black dresses. And this is where you can get into some interesting queries on the site for making recommendations, because you might know that somebody really likes this red dress, but they need a black dress for this upcoming occasion, and how do you make a recommendation for that? And essentially, it comes down to a mix of finding the related items, but also filtering it down to specific things. So I'm going to talk about some of the problems we hit besides filtering. One of them is vectors are big. Everyone should know this. About 2,000 vectors in a megabyte. We use usually 128 32-bit floats. Dense vectors don't compress. If you're using dense vectors, you can't really zip them up. If you can zip them up, they're not dense vectors. What this means is if you have a 5 gigabit pipe, so like a usual ECS or EC2 instance, you can only send about 1 million vectors over the wire. That might seem like a lot, but we have tens of millions of products. So we can't even do in 1 second all of our products. Brute forcing vectors is too slow for us. On my laptop, it takes about 400 milliseconds to do 1 million entities and get the top end results. Most of that's not the cosine distance, it's getting the top end results. This is actually faster than getting the million entities down. It took me a second to get the million entities from EC2 and half a second to compute it, but this is way slower than the 50 milliseconds I want. So we use approximate nearest neighbors. What this does is allows trading off accuracy for speed by pre-indexing the vectors. But the problems with that is most ANNs like Annoy, here's a link at the bottom, they keep the original vectors. So you have all the same vectors, all the same data you started with, but now you have an index on top. You actually have more space taken than you started with. There are some ANNs that will compress the vectors, like face, which is Facebook's, but you're just trading size for accuracy, and you can only compress so far down. Those aren't huge problems, but they add up later. A lot of them, if you update a vector, you have to rebuild the entire index. This can be a problem trying to keep up to date with things coming in and out of stock. And they don't natively support filtering. So if you build an index, it tends to be all your products in one index. Well, how do I get all the things that are only red dresses out of that index? So how do we filter them? The naive way to do this is post-filter. You go to your index, you get all the responses, and then you just throw away anything that's not a red dress. The problem with this is if the closest things to what you're looking for aren't red dresses, you might have to get 10,000 responses and hope that you get 10 red dresses in all of those. You still might not, especially when we have tens of millions of products. The second one is every filter combination you're looking for, red dresses, blue dresses, green dresses, you build a separate index that only has red dresses, blue dresses, green dresses. This ends up with a lot of indexes, but it works. So that just causes combinatorial explosion. We have a lot of different things that we look for. We look for categories, we have a bunch, we have colors, we have a bunch. You add those together, red dresses, white dresses, red shirts, black shirts, you get the picture. It's quite a few. The one that really bites us though is countries, where for the previous ones, the red dress is only in the red dress index. The blue dress is only in the blue dress index. You have a lot of indexes, but each index is fairly small. You add them all up and you have the same number of vectors. What happens with the countries, every product's in 35 countries. So you have an index for each country, so we actually have all of our vectors 35 times. It gets even worse if you do inverse filters. Inverse filters is something like, I want all the items that are not dresses. If you have 100 categories, and each one is 1% of your size, making 100 of these indexes is 99 times as big as the original index. So what this means is we can't pre-compute. You end up having to pre-compute results for all of the filter combinations that you want. At the end of the day, if you do 50 pre-computed results, you actually take the same size space as a vector does in the first place. So you might as well just store the vectors. And then every time any vector changes, so any product gets updated, we have to go find any other product that might be related to this product and try to update that as well. So the way we actually solve this. First off, we use an ANN index that does not store the vectors. So essentially you build up the index and you throw away the vectors after you've built the index. So the size of the index doesn't include the vectors anymore. The fact that the same product's in 10 different indexes doesn't matter because the index doesn't hold the vectors. So we create thousands of indices, probably more like millions, one for each filter combination. And then at query time, you go to find the index you need. You find the candidates based on that. Then you go get the actual vectors from a key value store and use the cosine distance, return top end results. And then the last thing that's very important is you have to keep those indices in the vectors as close to your serving as possible. If you don't keep them close to the serving, you end up with that thing of you can only get 1 million vectors over the wire every second. So the actual implementation. First off is RP Forest. This is open source. We wrote it at Lyst a couple years ago. It's an ANN that doesn't store vectors. So the problem with this one is you can't actually get the distances out of it. The only thing you can get out of it is candidates. So it knows for a given target what are the things that are probably closest to it. But they don't, at that point, know which one's the closest. But it's great for getting candidates. So if you just want like the 10,000 closest things, works great. And the size scales with the number of IDs. The vectors don't matter because it's all gone. Edna is our current recommender service. Here's the diagram of the entire thing. It's mostly based around this Postgres service over here, Postgres database. So the way it works is there are jobs that wake up, cron jobs, Airflow, doesn't matter, Metaflow we use. You read the interactions metadata out of the data lake. You make the indices, you make the vectors, you store them in Postgres database, and then at query time, Edna, the service itself, is really just a pass-through. It handles web requests, targets and filters come in, it goes to Postgres. Postgres, inside Postgres, in a Postgres extension with custom code, it does finding the RP forest index, the cosine distance calculations with the vectors, and returns you all the results. So, good things about this is it's pretty fast, 35 milliseconds. It's faster than the 50 milliseconds I asked for. It can handle near real-time updates. In practice, we don't really do it that fast anyway. But the vectors can be updated. It's a database. You can just upsert one row, and it works. You do have to rebuild the indices every once in a while, but that's not too hard. The main limitation is it's a centralized data store. You have one big Postgres database that handles all your requests. You can have as many web instances in front of it as you want. You still have to talk to that one Postgres. If you run out of resources on that Postgres, the only way to scale it is by a bigger one. And the other problem is A/B tests fight for resources. So if you're running on one model in Postgres, it pretty much caches all of it. If you suddenly add in a second model that has another 30 million or 40 million vectors, suddenly your Postgres is overloaded. And then both of them suffer. And it's hard to measure what's actually going on if suddenly your whole cluster gets slower when you run an A/B test. The custom Postgres extension is a problem as well. We use a lot of AWS. We run everything in EC2. All of our other services use RDS for their Postgres. We can't use RDS for this because RDS doesn't let you run custom Postgres code. The last problem is there's no history. I don't know what the vectors were last week because we always upsert. Every time we make a new vector, we just dump it in the database. The old one's gone. I have no idea what happened last month. So we thought we could do better. We can do better. We have a service called Augur. It's very similar, you can see, to the last one, except there's a couple more boxes. Same start, jobs wake up, read in action. They store the indices and vectors. Instead of in Postgres, they just dump them into S3. Lots of files, lots and lots of files in S3. But Amazon built S3 and it's good at files. This whole bottom box, by the way, is one Docker instance. This is one Docker container. All three of these run in the same thing. So there's a sync thread that runs in Docker inside Augur that just watches the S3 bucket that is set up for changes. If it sees changes, it downloads the files. When it downloads the files, it just dumps those files straight into a local database. So every instance of Augur has its own database. And it's just local. And then at serving time, you ask for a certain target and some filters. It goes to the local database. It gets the index it needs. It gets the target vectors it needs. It gets the, does the cosine distance calculations, finds the top end, gives you back the recommendations, and that's it. So just a note on the database I'm using, this is Lightning Memory Map Database. It's also open source. It's great. It's fast. It's super old school. It stores the entire database on disk like Berkeley DB does. It's only a key value store. It doesn't do anything else. There's no indices. There's no columns. You have a key, you have a value, that's it. That's all we need. We have an ID of a vector and we have a vector. That's it. What it does do that's cool is the DB file, once it creates it, it memory maps it in. So if you have an entire database that's only 12 gigs and you have 16 gigs of memory, the entire thing ends up in memory. So essentially it's a memory database. If you go over the size of your memory, that's fine, it'll just be a little bit slower for a while. We started out with JSON as our formats, but JSON's really, really slow. So we switched to binary serialization. We use protobuf for the API because it has a schema that's predefined. And as far as APIs go, you want a schema because anyone can look at the schema and know what you can call. But internally, we didn't want to use protobuf because then you're just like leaking implementation details everywhere. So we use message pack, which is much the same thing, but there's no schema. Strengths, it's fast, also faster than Edna, 20 milliseconds. This is fast enough for me. You can horizontally scale it. Since every single instance of this has its own database, if you have 100,000 requests, you just start a couple of them. If we suddenly have 200,000 requests, start twice as many nodes. Just kick up a few more machines. Each one runs on its own. Geographically distributed is the same thing. If you want to start running ones in Asia because you suddenly have a lot of traffic in Asia and you want them close to Asia, just start ones up in Asia. A/B testing can be done on like-for-like clusters. Instead of overloading the same nodes with 2 different sorts of embeddings, just start a new cluster that serves different embeddings and do some load balancing in front to choose which one you talk to. So they can have exactly the same scale and exactly the same response time. And since we're storing all the embeddings in S3, every time we write the embeddings, we write it in 2 places. You write it in the latest folder and you write it into a dated folder so you could store them forever. So we have a history now of what our embeddings have been doing over time. There's some limitations. First one is startup speed. Since it has everything in its local database, when it starts, it has to download everything. This can take some time. It's not really that much of a limitation because if you do rolling restarts, you shouldn't ever see this. You give the server time to start up and warm up before you start sending real traffic to it. It does only update as fast as S3 is updated. With the polling process, it can take it a couple minutes before it notices there's something new. Vertical scaling still requires larger nodes. If you run out of memory, you just have to get a bigger machine. Like all your nodes just have to get bigger. There is some future work in the plans. One is push notifications. Rather than polling S3, if we just push all the new vectors out to everything, we'll get pretty close to real time. We can do some amount of sharding if we split countries into different clusters. Some products don't exist in multiple places. And the last one is more speed optimization. We haven't done any caching on this. The 20 milliseconds is like no caching. I've spent no time actually trying to make this fast. Conclusions. Decentralized is better than centralized. Never put all your stuff into one database and then have everything talk to it. You will not be able to scale horizontally. Filters and ANNs are hard. If we didn't have to do filters, we could just brute force this. Because we do filters, we have this combinatorial explosion of how many things we have to keep. We have terabytes and terabytes of vectors. Think about your use cases before you design your infrastructure. This is related to the last one. If you know you have limitations, build your serving infrastructure around it. And separate your serving from your modeling. You don't have to know what your models are doing to serve that. If you just need to do cosine distance between vectors, just work on that. Leave the modeling to someone who knows how to do that better. And that's all I got. Any questions? And also we're hiring.
Another mic or? Yeah, first question at the back. Go for it.
I have 2 questions. Thanks for the talk. The first one is you actually stored the vector into S3 bucket. So just wondering, have you considered about the other solution like feature stores like Google's Feast, something like that to store your vectors, potentially embeddings in the future as well? So the second is about the filters. So you mentioned color and then category. So we're just wondering, do you have to predefine your filters? How about some more sentimental filters like I want oversized trousers. So the oversized obviously could not be in your product description, could be, but something that is not in your like particular column or fields, you know what I mean?
Yeah. For your first question, did we think of anything besides S3? We've looked at Redis. I think about Redis all the time. I haven't done it. I might do it at some point.
But there's lots of other having solutions about feature stores, like particularly storing deep learning embeddings. So, I mean, like, have you ever looked into those things?
Not too much. S3 is easy. And S3 is where we keep them. And S3 is cheap. And it works well enough. Yeah, we debated it. But at the end of the day, S3 is only there to keep it long enough for the actual node to go get it and load it into its own memory. So we're not actually serving anything out of S3. S3 is really just there as a storage. If we got something that was more responsive, it wouldn't really save us that much. Would we be able to load it faster into the local memory? I mean, honestly, probably not. Like, downloading a file from S3 to an EC2 instance takes no time. Like, no time. If you put it into Redis even, just the back and forth of like trying to get all the key values, rather than just downloading a file from S3 that has it all zipped into one thing, you'd actually take more time. Even though it's a more specific storage structure, it would take longer. For your second question, as far as different types of filters, we do have like style tags we're thinking about extending to, which has a lot more different types of things. Again, it's like another order of magnitude of data because we have a lot of different tags. And for that, again, products can be in a lot of different ones. Like you mentioned, oversized, right? So the oversized index can have a lot of items in it, and they have oversized trousers, red oversized trousers from Gucci. You have a lot of different indexes. So each time we add things, it takes more and more time. We can do some amount of post-filtering. If you can get down to an index that's close enough, post-filtering does work. Post-filtering just doesn't work when you're doing like a massive index. If you do all products and you try to post-filter, there's a good chance you won't get what you want. If you're just trying to find oversized trousers, well, you could go to the trousers index, get 10,000 results, and then try to limit it down to oversized. We do also use Elasticsearch for a lot of our search needs. It's kind of the other side of the equation as far as list goes. Most of our searches go to Elasticsearch, and that does just do whatever searches you want to do. Any amount of free text, anything that's in the description, it'll find it. It just doesn't work that well with the relatedness. What we can do, and we do sometimes, is we use Elasticsearch to get a bunch of candidates that match the filters that Elasticsearch wants. Then you send it off to Augur as a service to re-rank it based on the distance to the vectors. So it's kind of a hybrid approach. You have the same problem of maybe the most related thing isn't in your top results from Elasticsearch, though. So you end up with the same thing of you have to get a lot of results from Elasticsearch to send over to get re-ranked.
I'm just curious, have you guys, sorry, this is the last one, promise. Have you guys tried on the embedding space, all the filters, convert into embedding and do the embedding calculations? Sorry. I'll check with your data scientist.
Okay. There's a question at the back over here.
Hi. When you use horizontally scale Augur and the database is being pulled, right, every single time when you spin it up, do you have any problem with like this cold starting time? Because the way that how you have to pull the database, and if you do scale that, would that be a problem for you?
The cold start.
Yeah, the cold starting time for that.
Yeah, I mean, that was one of the limitations I mentioned. It does take it a few minutes before it gets up to speed with all of everything. I mean, as far as startup speed goes, I mean, we use Django for the web app. Django takes about 20 seconds to start. So I mean, just that takes 20 seconds. Starts responding, and then we actually load in. What we do is I skipped one step just for simplicity. I separate out the vectors. I grab the vectors that are most common and some of the ANNs that are most common, put those into one bucket, and I load those before the service even starts responding to health checks. So the service won't respond to a health check. It won't get any traffic from the load balancer until after it's loaded its initial set of vectors. At that point, it returns responses. It's not perfect because it's missing a good portion of the product space. But in the background sync thread, it'll catch up in 2 or 3 minutes.
But just out of interest, approximately how long does it normally take?
I mean, it takes about a minute to start before it starts responding to anything. And it can take about maybe 4 more minutes, 5 more minutes before it's like fully loaded. But I mean, after 2-3 minutes, you have most everything. Unless you hit like a really weird query, misses. Yeah, I mean, worst case, like if all the nodes went down and we had to just cold start the whole cluster, it would take maybe 5 minutes to get like back up to speed fully. But if you do rolling restarts, you don't actually hit that.